So, any questions or comments?
Now, this is supposed to be a forum for creativity, which is run around programs with discussions and questions. And I understand that in Japan, the culture is not always to talk. Ask questions. So I'm just trying to provoke you. You want to make this forum a success, you have to speak up.
Okay. So I have a question. So in your slide of indications of new physics, you haven't have the strong CP problem. I would like to hear your comment on that.
Well, there are many problems I didn't address.
Yeah.
The strong CP problem, of course, is one that has a simple solution that Peche and Quinn proposed years ago. It implies the existence of another dynamical field called the axion, and existence of a particle. Could very well be there. So far, we have no evidence for it, just like supersymmetry, just exclusions. I suppose I can't think of any other resolution for the CP problem. So
I feel that the Pecha-Quinn symmetry sounds very strange because it's only broken by the anomaly of the QCP.
well, you know, anomalies are called anomalies because they were in contradiction to what you expected. But they're just there. QC, you know, those anomalies are, you know, they're the effects that you, in a quantum field theory, if you approach it using Feynman rules perturbatively, you have certain things don't happen that could happen, and happen non-perturbatively, so we call them anomalies. The anomaly is not really a good term. It really only means that a certain way of, simple way of calculating doesn't produce the effect. So to say that it's just an anomaly is like saying, I don't know a good analogy, but it's there. It just can't be calculated perturbatively. So no, it's a perfectly good mechanism, and in fact, in the framework where we now, in this larger framework, certainly in string theory, it's absolutely natural. So in QCD there is a parameter called theta, an angle, which characterizes the vacuum structure, discovered many years ago, and it would contribute to ZB violating effect, so it has to be, it has been measured, if you want, to be very small, or zero, but for no good reason. And so it's a kind of theoretical problem once again. Why is it less than 10 to the minus 9? But in the broader framework, a parameter that appears in the Lagrangian should be always thought of as a dynamical object. And that's what Peche and Quinn said. It has its dynamics. And there's a mechanism for it to relax to a very small amount. Sounds reasonable to me. But axion, you know, experiments to discover an axion are extraordinarily important for this reason, and also for perhaps explaining dark matter and other. Andy.
I just wanted to make some comments about the axion. Mostly a quip, not too serious. But so the axion was designed to solve a fine-tuning problem of 1 part in 10 to the 10. And if I take Steve Weinberg's view of what that fine-tuning is, which is not what I think it is, but just that having a very different scale, well, the axion, F axion, is now fine-tuned to more than 1 part in 10 to the 10. by experiment. So in a sense, if you take that view, it no longer solves the problem that it was created to solve. But A, I don't take that view, that's why it's a quip. And B, I completely agree with you that we should think about all the parameters in Lagrangian as dynamical things in any case, and the axion does that. The second comment is actually there is an alternative, which is a Nelson bar type theory, which are kind of hideous, but they do sort of work.
Yeah. But anyway, searches for the axion are really important, and they're good examples of non-accelerator collider physics, which we're waiting for. And from what I gather, we're entering a domain where, a very important regime of axion existence is going to be probed in the next year or two.
Yeah, so I forgot I wanted to say that also. The ADMX experiment will, with some caveats, more or less either discover the axion or definitively rule it out as a dark matter candidate.
Right, as a dark matter candidate. But it could always still solve the problem and not be dark matter.
Questions, comments?
Thank you very much. It was a very interesting talk. And in the middle of the talk, you mentioned the most pessimistic scenario. But at the end, you're it seems to me that you're very optimistic. So do you think that the most pessimistic scenario is quite unlikely, or just did you ignore that?
It's very hard to assign probabilities to these events. The thing that bothers me is that the most pessimistic scenario is possible. I don't know of any strong observational arguments against it that would say, oh, that's crazy. So, and that's why one should be worried, and one of the strongest reasons why we must explore the multi-TV regime as much as we can before we get to the point where we have to honestly say, if we're an extreme pessimist, that we don't have a good strategy for the future, except precision experiments. So, yeah, I think it needs to be taken seriously. But there's another point that, that is important to remember, especially, is that we could just be missing something important. We don't have many clues for what we're missing, but that's always the case. If you're missing something, you can't think of something new. But it's certainly worthwhile especially for theorists now, and especially for young theorists who don't have the burden of past success, to contemplate totally different ideas. And we could be missing something. And if I look at what we've learned in the last few years with the Higgs sector, the only thing that I see that's vaguely suggestive of missing something, and it's not something particularly new, is all of these signs that we're close to an instability of the vacuum. We're close to a point where if you extrapolate the high energies, the coupling and all the dimensional parameters seem to vanish. We're close to what might be a unified conformal theory now. Maybe Joe will talk about that. He's thought about that. Doesn't seem to make sense, but it might be indicating that, might be a kind of clue that's an indication that there's something there that doesn't make sense with the usual way of thinking about things. So maybe one should be thinking in a different way, but nobody so far that I've heard has any new ideas. So there are a few things like that around that I would encourage young people to pursue instead of just playing around with the next zillionth iteration of supersymmetric models.
Any other questions, comments?
So I am not a physicist but a mathematician. So could I ask, is there any mathematical challenge to help you to establish a consistent uniform theory?
That's an interesting question. There is, of course, a prize, a Clay Millennium Prize in quantum chromodynamics to prove that QCD, my favorite theory, exists, is a well-defined mathematical framework and has the properties that it has, if you want. It's one way of putting that Clay challenge. That's regarded by people whose judgment I respect as a much harder problem than the Riemann conjecture, which is another Clay prize. Fundamental physics is full of mathematical edifices that are unproved. That's because we often know that things are true even though we can't prove them. And we're therefore not interested that much in proofs. We're more interested in truth. However, partly it's because the basic formulation of quantum field theory, of this framework I was discussing, quantum field theory, which now is growing in its scope and power, has very shaky mathematical foundations. Most of the interesting theories, like all the standard model, can't be really well defined mathematically. And many mathematicians have tried and failed. So yes, the answer is there's a lot that mathematicians could do, actually, because although we're not interested that much in proof, since we know it's true already, we are interested in tools and methods and deeper understanding that would allow us to calculate and understand the theoretical theories better. But also in the more exploratory areas of string, quantum field theory, whatever you want to call it, mathematicians, there are lots of fascinating mathematical issues. And in fact, that's an area where mathematicians and physicists are working together, algebraic geometry. So, new mathematics is required for some of these ideas and is being developed by new mathematics, by physicists and mathematicians often together. So yes.
Thank you very much. Any other questions, comments? Yeah, if not, I'd like to ask one question. So what is your take on this, the question of the fine-tuning of the standard model vis-a-vis the anthropic principles?
Well, I'll take the opportunity to give a little spiel on that. You know, the revival of the religion of anthropicism has been due to the measurement of the cosmological constant, which is so small, it seems, in anybody's natural units or expectations, that it only exists because, as you heard from Weinberg, a possible explanation is that we live in a multiverse, and in most portions of the multiverse we can't live, so we're not there, so that's why it's so small. So this is the problem, and it's often expressed in terms of, you know, the problem is reduced if you assume supersymmetry. Supersymmetry was the only explanation we ever had for why the vacuum energy density, the cosmological constant, was 0. And so its scale of breaking sets the scale, maybe, if it's there, supersymmetry. So, but no matter how you look at it, it's a very small number. Now, these small numbers are indeed, should be taken seriously because, but only if sort of you believe that the goal of physics should be to calculate all dimensionless parameters exactly, eventually. We have, and you know, the hierarchy problem, the electroweak scale is also such a small number, and it's one of the main motivations for supersymmetry and for the current goal of exploring the TV range to try to understand whether supersymmetry explains this or something else. But this is one that we think we can explain. The neutrino mass is another very small energy scale, which we think we can explain. But the one that we really have explained, as Steve remarked, was one of the ones that was originally introduced by Paul Dirac. So back in 1937, Dirac noticed that there were a lot of small ratios, like the size of the universe compared to the size of an atom, or the proton to Planck mass ratio. And Dirac could have invoked anthropic arguments. He could have said, well, the reason the proton mass is so small compared to the Planck mass is that if it was equal to the Planck mass, or 100 times the Planck mass, then you put together a few hundred protons, you'd get a black hole. So obviously, you can't have people unless this ratio is very, very small. And you could probably estimate how many, you need to have stars, and then you need to have planets, you need to have people. How many protons do you need to put together before you get black holes? Sort of governs the size of complex objects that might think and ask these questions. But Dirac did not invoke anthropic arguments. I'm sure he'd heard of them because these ideas have been going around for even the 19th century. Dirac did make a suggestion. He said this ratio was related to other small numbers, like the size of the atom compared to the size of the universe. And then he made a prediction, and that's what's nice about Dirac compared to anthropic arguments. Good, they make you feel good. How do they make you? They make you feel good because you can then say, okay, I don't have to solve this problem. I can't solve it. There is no solution. I can just do something else and not feel guilty because there is no solution. We just happen to be in the universe that allows us to ask these questions. So Dirac didn't do that. And instead, he made a prediction. He predicted that since the size of the universe is growing, then the size of atoms must be growing, and that can happen if, for example, the fine structure constant varies with time. So he suggested look for cosmological time evolution of alpha, of the fine structure constant, and of Newton's constant, and those tests were done. You could measure spectral lines of distant galaxies or radioactive decays of naturally occurring uranium reactors on Earth, which have been around for billions of years. And you could actually rule out Dirac's prediction of the equality of all the small numbers. But what I'm mostly proud of is that this problem, Dirac's problem of the Planck mass to the proton mass, is solved by QCD, as Weinberg remarked. Because of the variation of the coupling, if you just assume that at a unification scale, the strong coupling is order alpha or something like that, then the proton mass is determined by the point, the energy scale at which the force between the quarks becomes big enough to hold them in, define the size of the nucleon, and thereby its mass. And so proton mass compared to unification or Planck mass is an exponential of minus the inverse of the coupling at the unification scale, which is the right order of magnitude. So this is the logarithmic trick, but it's not a trick. It's a fact of nature. The logarithmic variation of the couplings with energy. And not only is it a fact of nature that determines the scale, this 10 to the minus 19, that makes us possible to put together people without forming black holes, it's also now our tragedy that we face as high-energy physicists. Because to get up to here, we have, it's the opposite, exponentially far away. Things vary, physics varies on a logarithmic scale. The cost of machines varies some quadratic energy scale. And it's the disparity between that that's our problem. So anyway, that's an example of how to calculate these small numbers. And as I said, we have the other examples, such as the electroweak scale, and we might have such an explanation. Neutrinos, we might have an explanation. The only one we might not have an explanation so far with our old ideas is this cosmological constant. And the problem is we don't know what the answer is. But that, I don't think, is an argument for giving up, which is what the entropic principle is. It's simply saying there is no answer within physics. It's just, there are many other reasons to object to the use of entropic arguments in science, in general, in physics in particular, both technical and conceptual, but I could go on for a long time in that direction, but I won't.
Thank you very much. Any other questions? We have some more time. Okay.
Thank you very much for that nice discussion. Just to say that I'm an observational astronomer, so I'm not really detailed in these things, so I hope my question is not too stupid. My question is, well, listening to Professor Weinberg's talks and your talks, I somehow feel that, like, right now, the current status of, like, the theoretical physics is to modify the current, like, standard, or, like, to add some things to the formulas to fix the observations. Well, looking into history, like, going back, like, from Ptolemy's time to, like, Kepler, that, like, he added the epicycles to the solar planets just to fix the observations of, like, the rotation of Mars, the orbit of Mars. My question is that, like, in your view, like, in current theoretical physics, what's the proposal that, like, shakes the core foundation and changes? Like, what Kepler changed in the planetary model was to change a circle with an ellipse, something no one even thought of for 1,500 years. So, is there such a, like, very core fundamental thing that everyone is accepting without question?
Well, there are, and I actually hinted at some of them, but those epicycles weren't a bad idea. They were sort of like effective field theory. You add extra Fourier components to your perturbation amount. It was and it worked better than. Now it turns out that ellipses are a good approximation, and it was partly, ellipses But the theoretical framework wasn't there until Newton. So one of the reasons Kepler was so successful was that Newton explained it and calculated it.
Well, after.
So, excuse me?
After Newton was like,
But, right, but, you know, if Kepler had been wrong, Newton would have found the right. So, you know.
I mean, like the cycles were misleading.
Well, they weren't. No. They weren't misleading. Circles were, you know, good first approximation, and then you start adding corrections systematically. And, you know, there's no question that with epicycles, which are sort of, you could, with enough epi. So it's very much like the attitude that, I'm not sure this will satisfy you if you don't know what Weinberg was talking about, of effective field theory, the way he was describing how you might try to go beyond the standard model. Now, the standard theory, in many of its, you know, is very spare in its parameters, but if you put it in this framework of quantum field theory and regard it as just describing physics of the energies we know and not knowing what would be the corrections might be at higher energies, then that depends on the scale, on you know, a scale of where new physics is. And there is a systematic way of adding corrections. You might regard that very much like epicycles. And in fact, but it is a good way of trying to parameterize where you might look, tell experimentalists where to look for new effects. So, you know, you have those coefficients of the epicycles, go out and measure them, and the same is what we tell. Now, it's better yet to have an idea that organizes them all and turns the circles into ellipses. And there are such ideas as well, some of them at various levels of sophistication. Now, I was also, did remark on the fact that certain more theoretical concerns, like quantum gravity, like bringing gravity into this framework, do raise deep questions about many of the foundational principles of the framework we're using. Okay? And that might lead us to, we hope, to, but you know, there's nothing wrong with the idea of adding epicycles as a way to parameterize deviations from circles or the standard model, a way to inform observers what to look for and how to organize their observations. So that's normal science, but at the same time, you want to look for places where your principles are being challenged, or new ways of looking at things that might allow you to, at one step, get an ellipse from a circle instead of getting it by adding a bunch of epicycles.
Any other questions? Comments? Okay. If not, let's thank the Professor Gross again.